I want to present a different approach to the additional F test problem from section 8.4.1. The way the textbook presents this approach is somewhat confusing, at least in my opinion, somewhat confusing. We could have a more direct approach and probably less confusing. Again, we have the baseball salaries, and we have 5 different independent variables that we are considering: years in the major leagues, career ERA, innings pitched, career wins, and career losses. So I'm going to skip straight to the additional F test problem only, and this is from sheet 2 in the original Excel file. So if you go down to the testing of group coefficients, so this is where I'm going to present a slightly different approach, but we finally end up with the same answers, of course. So here we want to test of those 5 X variables, we want to test just 2 of them, the significance of just 2 of them. So if we want to test the significance of the entire set, X1 through X5, so we have an F test. So we've already seen that. And if you want to test individual X values, taking one X at a time, then we have a T test, and we have seen that also. But if you take a group of variables at a time, sometimes this will be very useful when you have kind of a related set of variables and you want to either keep the entire set in the model, or you have to take the entire set out of the model. So how do you test the significance of that group? So here, let's assume that we want to test whether the number of wins and number of losses, and that's X sub 4 and X sub 5, okay, is that as a group significant in the model or not? So what we are trying to test here is whether beta sub 4 equal to beta sub 5 equal to 0, both taken at a time, as against at least one of the 2 betas is not equal to 0. So that's what we want to test. Now, we're going to define the full model. We're going to define model 1 and model 0 like it is in the textbook, but I want to do it with different terminologies. I think that would be useful. So we always start with the full model, which is what your textbook calls as model 1. So you have all the variables in. So that's going to be our bottom line. That's the baseline to which we're going to make the comparison. So our model 1 is the entire model. So we have all the x's, x sub 1 through x sub 5. Now, from this model, you prepare a partial model. So now what we're going to do is, we're going to take the variables that we are interested in. So we want to test whether x sub 4 and x sub 5's coefficients are both 0. In other words, whether x sub 4 and x sub 5, the wins and losses, is that taken as a group significant or not? So we'll pop out those 2 variables. We'll take x sub 4 and x sub 5 out of it. Then what we end up with is our partial model. And your textbook calls that model 0. We'll call that partial model. Okay? So we have only x sub 1, 2, 3, and the subscript 1 is missing. Okay, let's put that subscript 1 there. So remember, we have to compare when you're given these 2 models, full model and partial model, and if you're asked to answer which variables significance are we trying to test, then you have to compare these 2 models and see which variables are missing in the partial model. So when you compare these 2, the variables that are missing are x sub 4 and x sub 5, and that's what we're testing the significance for, x sub 4 and x sub 5. Okay. So let's define sum of squares. So let's call SSE sub f as the sum of squares of error for the full model, and SSE sub p as the sum of squares for the partial model. So SSE from this model is SSE sub f. This is SSE sub p. Okay. Now you notice that SSF contains all the variables, and the partial model is going to be a subset of the full model, and therefore SSE of the full model will always be smaller because we're taking some variables out of the full model to get to the partial model, and therefore the error, when you take some variables out, the error will increase. So SSE sub f is always going to be smaller than SSE sub p. So that difference, when you take the difference between these two, and that is the amount of sum of squares that is attributable to these two variables that we have taken out. When you take these two variables out, your sum of squares of error increases by the difference in these two errors. So that's the sum of squares attributable to the two variables that we have taken out. Okay. So SSE that is attributable to the two variables missing in the partial model is equal to the difference in the two sum of squares. So that difference in sum of squares of error, so that the sum of squares attributable to these two variables has a degrees of freedom exactly equal to the number of variables that contributes to that SSE increase or reduction. So how many variables are there? There are two of them. So that is, the degrees of freedom is 2. So when you divide this SSE by the corresponding degrees of freedom, you get the MSE corresponding to those two variables. Okay? So you take that SSE and divide by the degrees of freedom and you get your MSE. So if you divide that MSE, that is MSE attributable to these two variables alone, the MSE attributable to the variables that you have removed from the full model, okay, the variables that you are interested in testing, and you divide that MSE by the MSE of the full model. Remember, the full model is the basis with which we are comparing, and that is called the partial F. Okay? So now the degrees of freedom for the numerator is 2. The denominator is the degrees of freedom that comes from the full model, the degrees of freedom of the error, the SSE degrees of freedom for the full model. So this way you don't have to think, try to figure out n minus q minus k minus q and that kind of stuff, which is kind of confusing. So this is more straightforward. How many variables you're testing for, that's your degrees of freedom for the numerator. And you go to the full model and look at the degrees of freedom for SSE, that's the degrees of freedom for the denominator. Okay. So let's generate results using LinEst. Okay. So we're going to look at the entire data set. So that is starting from years to, so from O through S, and salary being the Y range. So we have LinEst, salary, and then all the X variables taken together. Okay. Then do Control Shift Enter and we get the results for the full model. Now the partial model, okay, remember, is we're going to take R and S out, win and losses out. So it will be only be O, P and Q. Okay. So LinEst, again salary being the Y range, O, P and Q alone. We have now left out win and losses. Now press Control Shift Enter. So now we have the partial model. So now SSE of the full model is here. SSE of the partial model is here. So SSE for the variables that were taken out of the full model then is the difference between these two. Remember, SSE sub P will always be larger than SSE sub F. Now degrees of freedom, now it's going to be 2 because that's the number of variables we took out. Now MSE for the variables that we are interested in is that SSE of the variable group and the number of variables in the variable group. So that's our MSE, and the degrees of freedom here is 2 corresponding to that. Now, MSE, the full model, okay, so that is your SSE of the full model divided by the degrees of freedom corresponding with that SSE for the full model. And the degrees of freedom for that is that. Okay. So now we have the numerator and the denominator that we need for partial F. So MSE of the variables that you are interested in divided by MSE of the full model. That's our partial F. Now the p-value is f dot dis dot RT of that F, and the 2 degrees of freedoms come from here and here. And that's the p-value for us. So now we are not going to be able to reject because p-value is very large. So since p-value is greater than 5%, we cannot reject the null hypothesis. So do not reject. And then we have to interpret, that is, we do not have sufficient evidence to conclude that the 2 variables, win and losses, taken as a group, okay, is significant. The group is significant in the regression. If we did conclude that they are significant, then the probability that we are wrong is going to be 40.62%. So I feel that this is a more direct way of looking at it instead of the way the models are described in your textbook. So the basis is you always have the entire model, the full set of the variables in it. So that's the basis. So that gives us the denominator in the F. So you have the full model SSE, full model degrees of freedom, and then you have divide the degrees of freedom into SSE, you get the full model MSE. And then for the numerator, you take the full model and take out the variables that you want to test. Because when you take the variables of interest out, you want to look at what happens to the SSE, which is then going to be related to, so that's what the variable group is contributing in terms of, the sum of squares being done. When you put it back, that's the amount of sum of squares error is going to come down. So that's where the connection is. So you take the difference between the 2 SSEs, that's what is attributable to the variables of interest, and you divide by the number of variables, which is the degrees of freedom, and you get your MSE. So this is a more straightforward way of looking at the same thing. So if you follow the notations given in your textbook, you end up with the same answer finally. But I feel that this explanation is a little more direct. Hope you find it the same way too.